Hello and welcome back. So we'll look at a few problems involving entropy and the second law. But before that, I'll just discuss about how you can get a reversible process uh, which is general. So for example, while discussing about the Clausius's inequality and so on, we discussed about isothermal and isentropic processes. So, in an isothermal process, because heat addition is at constant temperature, we can reverse the heat addition easily, at least in theory, and assuming there is no friction, we can get a reversible process. So, if I have, for example, a process which is at constant temperature, let us say I have from 1 to 2, this line would be parallel to the S axis because the temperature is constant at whatever is the value here. So, in principle, if I do not have any irreversibilities because of either chemical reactions or friction or so on, I can do this process in the reverse direction and either transfer heat into the system or outside the system. So, we discussed that we can have isothermal processes of this kind. We also discussed that we can have isentropic processes. So, in an isentropic process, we said it is both adiabatic as well as reversible. So, let us say a process of this kind. So, there is no friction, therefore, it is reversible. There is adiabatic, there is no heat transfer. So, I should be able to reverse this process also and go from 3 to 1. So, I can get an isentropic process which is reversible and an isothermal process which may be reversible. So, what we discussed also is that we can have irreversibilities if we have temperature gradients or temperature differences over which we transfer heat. So, we said if we have a finite temperature gradient, then heat transfer across that is irreversible, because if we want to transfer back the heat, we would need to run a heat pump, because the second law says that we cannot transfer heat from a low temperature to a high temperature in a cycle without doing work. So, if I had an object which is hot and it was transferring heat out to the surroundings which are cold, then if I want to make this object and it comes back, all of it comes to the same temperature. If I want to make this object hot again, I have to transfer heat from the surroundings, and if I want to transfer heat from the surroundings, I need to run some kind of heat pump for which I need to do work, and therefore this process is not reversible. So, I cannot transfer heat with some gradient and then have a reversible process. So, now the question is, what happens if I want to have, for example, a constant pressure process with heat addition? So, how do I get a reversible constant pressure process? So, if I want to have a constant pressure process like this with heat addition, so what I should ideally have is the device outside which is transferring heat, whose temperature is also changing in the same way in which the system's temperature is changing, so that locally any heat which is transferred is happening reversibly. So, one way to look at these would be to acknowledge that in the isentropic process, we do not have any heat transfer, therefore, we can have it reversible and there is no heat transfer. So, there is no problem with temperature gradients being there because there is no heat transfer, or we need to have isothermal heat transfer. So, which means that if we can think of, for example, a combination of isotherms and isentropes, and we want to, for example, get a curve like this. In principle, we can think of these curves being extremely close apart, so that any heat transfer is very small, or any difference between 2 points is so small that everything is reversible. So, if I want, for example, an isobar of this kind, I can think of it as a combination of maybe going in this fashion. So, let us say I have isothermal heat transfer and then I have adiabatic reversible process, then I again have isothermal heat transfer and then I have an adiabatic process and so on. So, I can think of this isobar as being made in this fashion by a combination of isothermal and adiabatic processes. So, if these were really closely spaced together. So I could think of this as being a combination of isobars and reversible adibats, which then gives me any process of this kind. So depending on how I space these vertical lines and the horizontal lines, I can use different combinations of isentropic processes and isothermal processes to get either a constant pressure line or a constant volume line or so on either a TS or a PV diagram. So that is one way in which we would be able to get reversible processes other than isothermal and isentropic processes by using a combination of these. So having seen that, let us now go on to solving some of the problems here. So here it says a system consists of 2 meter cube of hydrogen. Okay, so I have a system. It says 2 meter cube is the volume, the gas is hydrogen. Molecular weight of hydrogen is 2 kg per kilomole. Ratio of specific heats is 1.4. It says this is initially at 35 degrees centigrade. And initial pressure is 215 kilopascal. This is contained in a closed rigid tank. Okay. So it's rigid tank, therefore there are no changes in volume. It is closed, therefore mass is constant. Energy is transferred to the system from a reservoir. Okay, so I have energy being transferred here from a reservoir at 300 degrees. So reservoir is like a really huge quantity of something such that the temperature does not change when you transfer energy out. So this reservoir is at 300 degrees centigrade. Energy is transferred until the temperature is 160 degrees centigrade. So I have energy transferred due to a difference in temperature. So I would call this as heat. So we have T2 for the hydrogen as being 160 degrees centigrade. The temperature of the system boundary where the heat transfer occurs is 300 degrees centigrade. So the boundary here is at 300 where the temperature where the energy transfer occurs. We are asked to determine the change in entropy of the system and the reservoir and the change in entropy of the universe. So we are asked to find out this. So I want to find out the change in entropy of the hydrogen first. So I have the TdS relationships. I also have TdS as dH minus VdP. This is for the hydrogen, it's a constant volume process because it's a rigid tank. So I can use this expression, constant volume process, this is 0, dV is 0 because V is not changing. So I have this. I can treat hydrogen as an ideal gas. So I can write TdS is equal to Cv dt because for an ideal gas du is Cv dt. I am assuming that Cv is constant and I am going to integrate this. I take T to the other side. Now I can integrate. So I get delta S. If I assume Cv is constant, I get Cv ln T2 by T1 and delta capital S is m into Cv times ln T2 by T1. So the mass is not given, but I know this is an ideal gas, which means I can use the ideal gas equation of state. I need to find out m. The pressure is given as 215 kilopascals. That's 2 and 5 10.3 pascals. The volume is given as 2 meter cube. R is 8314.5 divided by molecular weight. Molecular weight is 2 kg per kilomole. This is R, and the initial temperature was 35 degrees. that's 35 plus 273 in Kelvin. So this is the initial mass, and the mass does not change. So the final mass should be the same. So let me find out. So what I find is that the mass is 33.58 kilogram, if I have not made any mistake. So that I think seems to be right. So this is 33.58 into CV. CV is R by gamma minus 1. So maybe let me go on to the next page. CV for an ideal gas is R by gamma minus 1. So R is A314.5 divided by R is R bar by molecular weight. So that's A314.5 divided by 2 in this case. Gamma is 1.4. So gamma minus 1 is 1.4 minus 1. So this comes out to be about 10,393 joule per kg Kelvin. So I am going to use this. The final temperature I have is 160, which is essentially 433 Kelvin. The initial temperature I have is 35, which is 308 Kelvin. This gives me a value of 118.8 kilojoule per Kelvin.
So the mass is 0.38.
Apparently I have made a mistake in the calculation of mass here. Let me just confirm that. Okay, I think I put the decimal at the wrong place. So this is 0.3358. So this is 0.335. So I am guessing this comes out to be 1.18. I was using it as 33 and I got, I think, 118. So this must be about 1.18 kilojoule per Kelvin. So this is the change in entropy for the hydrogen, because the temperature of the hydrogen is changing as we are transferring heat to it. The only heat transfer in this case is from this reservoir to the hydrogen. The rest of the atmosphere does not change. So we can find out what is the change in entropy of the reservoir. For the hydrogen here, heat is coming in, so the entropy is increasing, so delta S is positive. We can see what is the change in entropy of the reservoir. Okay, so in order to find out the change in entropy of the reservoir, we need to know how much is the heat transfer. We can consider this reservoir to be at constant temperature. So it's an isothermal process. So the amount of heat transferred from the reservoir, the heat is being transferred at a constant temperature. The boundary into which it is being transferred is also at 300 it's at 300 degrees centigrade. The reservoir is also at 300 degrees centigrade. So, what we can assume is that for the reservoir the heat transfer is reversible. So, if we consider that to be reversible, then what we know is that T into delta S is Q reversible. So, for the reservoir we can assume this to be reversible, then delta S is essentially Q reversible by T. It is happening at constant temperature of 300 degrees centigrade, which is essentially 673 Kelvin. But we do not know what is the heat transferred. We can find out how much is the heat transferred for the hydrogen. So, it must be the same amount of heat which is here. So, we can, the hydrogen is undergoing a constant volume process. We can write the first law for the hydrogen. So, what we see is that from the first law we have dE. In this case there is no change in kinetic and potential energy. So, I can replace it by du is essentially del Q minus del W. For the hydrogen it is a rigid chamber, there is no electrical mechanical work, there is no displacement work, it is a rigid chamber, there is no shaft work and so on. This would be generally PdV and dV is 0. So, this is 0. So, del Q is essentially du or Q is delta U, and that is for an ideal gas mCV into delta T. So, I have 0.33 kg into CV is 10393, we just found that, into delta T is for the hydrogen is 160 minus 35. Since it is only a difference of temperatures, it does not matter whether I take it in centigrade or in Kelvin. So, this is this comes out to be 428 kilojoules. T2 is greater than T1, delta T is positive. This is energy coming into the hydrogen, which is positive for the hydrogen system. For the surroundings or the reservoir, the heat transfer is negative because it is heat going out of the reservoir. So, this is essentially minus 428 Kelvin, sorry, minus 428 kilojoules divided by 673 Kelvin. Which gives me a value of 0.637 kilojoule per Kelvin with a minus sign in front because this minus sign is there on top. So, this is what I see, and if I look at the entropy change for the universe, it is essentially entropy change for the system plus entropy change for the reservoir. So, for the system we just found that out, it was 1.18 kilojoule per Kelvin and this is minus 0.637. Which is 0.543 kilojoule per Kelvin. So, what we see is that the entropy of the universe is increasing by this amount when we have this heat transfer. So, in this problem what we have done is we have assumed that because this is at a constant temperature and the temperature here is also the same as this. So, we have assumed that the heat transfer as far as the reservoir is concerned is reversible. The heat transfer as far as the process in this hydrogen chamber is irreversible. So, we see there is a difference in the entropy changes of these two, and the net effect is to increase the entropy of the universe, which is essentially what we expect as a consequence of the second law.